This is a production of Cornell University.
All right, once we figure out what's there, we basically have to make some decisions about what we're going to be using to get those nutrients into place. Okay? Now, those decisions are based on nutrient availability, and so you've seen this slide before, but we're looking at the concentration of the nutrients in the solution, the speed of nutrient replacement, as well as the mobility of that nutrient. Okay, so what are the decisions that or the things that we need to think about? Well, first is, from a fertilizer's perspective, we need to understand how much nutrient is actually in that fertilizer. Okay? We have basically generally two different types of fertilizers that are on the market. Okay? One is sort of complete fertilizers, which is sort of like a broad spectrum vitamin. You know, it's a broad spectrum nutrients. It's multi-nutrient or like a multivitamin. Okay? The problem here is this is generally not cost efficient for commercial growers. Okay? If I get a multivitamin and I put it in my body, some of those nutrients that are in that vitamin I'm going to be using, but a lot of it's going to be basically coming out, you know, into the toilet, right? Okay? Well, from a farmer's perspective, that stuff that's going out as pee is basically waste. Okay? Now, from a gardener's perspective, that may not be problematic because you got to think about how this stuff costs and the convenience of its use. We have simple fertilizers, which is basically it's providing one nutrient or maybe two nutrients. From a farmer's perspective, because they're buying in bulk and they need to maximize their dollars, that might make sense. But from a home gardener's perspective, that's totally off the charts. I need to have a little bit of this, a little bit of that, a little bit of this. I need to do the math to figure out what it is. Why? I mean, how many of you guys take just vitamin A or just vitamin B? Most of us, when we took stuff, we're taking multivitamins, right? Broad spectrum approach. Okay? All right. The next thing that we need to think about is we need to think about the release rates, how fast this stuff is going to go off. Okay? It's going to not go off. How fast this stuff is going to become available. All right? Most inorganic fertilizers have a very fast release rate. That's not true for all of them. There's a couple that are slow. Rock phosphate is a good example of that. Okay? But they release very fast. And if they release very fast, this can be somewhat problematic. Okay? If I put it out there and it releases fast and my plants are not prepared to take all of that nutrient, where's that nutrient going to be going? Downstream. Okay? On the other hand, we can potentially have slow release. Most of the organic fertilizers release fairly slowly. Okay? Mineralization is slow because of decomposition rates. Now, this is a good thing because I'm not necessarily going to lose it from the system, but what's a possible negative to this? It might not be supplying enough for the plants at their moment of need. Okay? So most operations are thinking about a combination of these things. There's advantages and disadvantages of it. Now, Dillman Hill, we aren't using the inorganic because we're trying to do it more of an organic operation, and part of the philosophy is we're going to be using organic sources. Okay? Well, you guys saw the results of the nutrient analysis. They have a lot of availability. Well, why? How do they overcome this slow release? They go with abundance. Right? Okay. All right, other considerations. Availability and cost. And really, the reality is I probably should have separated these out. Okay? Certainly, you can understand the cost. If something's more expensive than another, I'm not going to, I get better bang for my buck if I go with less expensive stuff. But just because something is more expensive doesn't necessarily mean you're getting less value from it or potentially more value from it. Okay? You actually have to think about what the spec is of that fertilizer, the NPK. Okay? Let's use this for example. Okay, I've got a fertilizer that's 10, 10, 10, and a fertilizer that's 20, 20, 20. I don't know what fertilizer. It's just those are the specs on them, all right? Okay. This one costs $10. Or make it 100, which is more a little bit more reasonable. $100. Okay. This one, that's for a poor 100-pound bag. Okay, so 100 pounds. Okay, this one costs $150 per 100-pound bag. This one's more expensive, but for half again the price, I'm getting 2 times the value. Does that make sense? So in this scenario, if I needed to get 10, 10, 10 on my field, I could just sort of cut this in half, and I get a cheaper price. Does that make sense? Question?
Do they take into account the availability of the plants? Say if like number 1 was more like a form that plants could take up?
They do take that into account, and that's this effectiveness thing. There's sort of these release rates. Sorry. So the 10, 10, 10 or the 20, 20, 20 represent this, the nutrient content. The release rates and availability, that basically represents this component, the release, literally release rates, okay? So they're thinking right there, they're thinking, what's my nutrient content? And in that fertilizer, they're going to have an understanding about how quickly it's going to get to my plants, or how slowly. They also need to think, this issue of cost. Okay, those two could be basically, the 20, 20, 20 could be just concentrated 10, 10, 10. It literally could be the same thing, just concentrated. Or it could be something different. And that's where they're going to start thinking about the spec and the release rates. Okay, now, I've been mostly focusing on cost, but you also have to think about availability. Okay, in the United States, pretty much anything we want, we can probably get fertilizer-wise. We may have to pay for it, but there are major parts of this world that they can't necessarily get any kind of fertilizer they want. Okay, they may be able to get the rock phosphate, for example, here. They may be able to get the rock phosphate, but they probably can't get the sulfur-coated urea. Okay, that's a consideration that they need to take into account for their fertilizer applications. Okay, and that's where availability comes in. Okay, now, if you think also about this cost and availability, you also need to think about the cost and availability of transport and application. Okay, the example that I have here is if I have lots of organic matter. Okay, the reality is most organic matter has a lower spec, a lower analysis than some of these inorganic materials. And if I have to get 100 tons of nitrogen on my field, that might be 1,000 tons of organic matter. On the other hand, it might be 100 pounds of, well, it can't be 100 pounds, but it could be a different type of fertilizer that has a higher concentration. Okay, so not only do you have to think about the higher concentration when you talk about costs, but you also have to think about that higher concentration and the bulk of the material, how you're actually going to be able to transport it, which comes into this idea of convenience and ease of use. Okay? If I have something that is really bulky, I have to have the equipment to move it. On the other hand, if I have something like anhydrous ammonia, which is basically a liquid, I actually have to have the equipment to apply that. Okay? Great, I can buy this really cheap. Anhydrous ammonia, no, liquid gas, sorry. Might be able to get this really cheap, but if I don't have the equipment to get this in the field, I basically just have big containers of expensive stuff. Right? Does that make sense? Okay. Urea, on the other hand, is ammonia, basically ammonia-based stuff. Urea, on the other hand, I can broadcast spread if I needed to. So if I don't have the injection equipment, okay. So right there is another decision that's going to be based on the issue of how I'm going to get the nutrients in there, how expensive it is, can I get it, and how am I going to be putting it on the field. Does this make sense to everybody? The last thing that they really think a lot about is this issue of side effects. Okay? if you guys remember those nutrient analysis results that we got back from Agro 1, all right, there were recommendations on how you actually apply the stuff. It wasn't just what you apply, but how you apply it. A lot of that how you apply it has to do with issues of side effects or waste. Okay? Certainly, if we put a lot of fertilizer on there at one time, theoretically we can get a lot of soluble salts, which potentially will damage the plants and the microbes as well as the other fauna that are in the soil. Okay? Another example is organic matter. If I'm not organic matter per se, well, if I'm applying barn waste, manure, okay, and it's coming out as a slurry, and I'm applying it to my fields, I could theoretically seal my soils. I could clog them, okay? And if I clog my soils, I potentially can have anoxic conditions. If I have anoxic conditions, I can produce organic byproducts that could actually be toxic. I start seeing ammonia. The ammonia starts damaging my roots and my plants. Okay, does that make sense? Okay, it's not that organic matter is bad or the salt that you put up here. It's actually how you apply it and its byproducts. Go. It's coming from the fertilizer. Yeah, so as the fertilizer decomposes or becomes available, those salts, depending on the rate of, I mean, classically, we generally associate this with inorganic fertilizers. But you guys saw with the mulch products, the compost products, they had fairly high salts in them. You had to remember the high pHs that you got off of the compost? That had high salts in it as well. So you have to think about these. It doesn't matter what the source is, you have to think about the possible salt solution coming, or the salts coming from this material. Does that answer your question? You can ask a follow-up question.
How do you know, is there a type of fertilizer, let's say chemical fertilizer, that has more tendency to have salts? Or?
Is there, so the question is there a chemical fertilizer that has more tendency to have salts? Well, all of them are salts. So I think it has more to do with how you apply it. If you pick the fertilizer, if you put too much of it in, you're going to get the salts that are going to kill stuff. So I think part of the consideration here when you think about the soluble salts is thinking about what my material is and what my plant needs are, and providing the nutrients, whether it's inorganic or organic, or nitrogen, phosphorus, potassium, whatever it is, to apply it at a rate that meets the needs of the plant, and I am not, in essence, wasting it. Okay? Because this is waste. Yeah, we can talk about the toxic effects of it, but if I'm getting this kind of stuff, I'm wasting my fertilizer, whether it's clogging, whether it's salt buildups, whatever it happens to be. Does that make sense? Okay. Obviously, there's the issue of leaching when you start talking about nitrates and stuff like that. So, and when we get high levels of phosphorus, this stuff gets into the groundwater and this moves out of the system. Okay? Also, we talked about this when we are talking about bringing nutrients into a plant. Do you guys remember the difference between if the nitrogen source is a nitrate versus an ammonia, the plants are going to be using different types of proton pumps? Okay? If we are putting in an ammonia fertilizer, we're basically going to be acidifying our soils. Now, it may be very local and it may not be that big of a deal, but if your fertilizer source is ammonia, the ammonia needs to get into the plant via proton pump, okay? Which means the ammonia is coming in, but protons are going out. And if the protons are going out, they're basically going to be acidifying the rhizosphere, right? Now, if I wanted to counteract that, maybe I should be thinking about using nitrate as my end source. Because I put the nitrate in, it's a negatively charged ion, and potentially the protons are going to be coming in to maintain that charge balance, right? And if I'm pulling protons out of the soil solution, I'm raising the pH around my rhizospheres. Does that make sense? So these are side effects that you have to think about. The last thing is you also have to think about secondary deficiencies. This goes back to that barrel analogy. Okay? You guys remember the barrel analogy with the slats in it? Okay? If I if my nutrient of my nutrient of deficiency, or the most limiting nutrient is nitrogen, and I say, okay, I'm going to put nitrogen fertilizer in the system to where I'm going to get optimum growth, you may not, in fact, get optimum growth. Why? Well, go back to the barrel analogy. We'll make this a really big barrel with just 2 slats. Okay, here's my barrel. Okay? And this barrel, for whatever reason, just has 2 slats. One of them happens to be nitrogen, the other one happens to be phosphorus. Right? Well, if these slats, nitrogen is right here, and phosphorus is right here. You guys see the difference there? Yeah? And I say, okay, well, I'm going to get nitrogen, all the nitrogen it needs. I'm going to make this slat all the way up here. So my nitrogen is now up here. I'm not going to get the response I expect, because phosphorus is now limiting. I went right think about these secondary deficiencies. Does that make sense to everybody? Okay.
This has been a production of Cornell University, on the web at cornell.edu.